In this video, we solve problem 7.6.022 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the moments about the x-axis, the y-axis, and then the center of mass, x bar, y bar, for the lamina of uniform density rho bounded by the graphs of the equations. So what I would recommend that you do to get started is graph the lamina itself. So you're going to graph the region bounded by those two functions. Now, when you see those functions, my hope is that you have some sense of what this graph is already going to look like. This function is a function of the form y equals mx plus b. So we know that that's a line. We know that when x equals 0, y equals 1. So that's the y-intercept. And then we're going to go up 1 and over 5, up 1 and over 5, up 1 and over 5 to find other points on this line. Now, I'm not going to draw this to scale. I'm just going to draw kind of a cartoon of our region here. We've got one line there. And then this second curve, hopefully you recognize that as the square root of x plus 1. And when you see the square root of x plus 1, my hope is that you have this graph, y equals the square root of x, in your head. That you say, oh, that's going to be square root of x. And then when I take all of those y values and I add 1 to them, it's just going to move the graph up 1 unit. So instead of starting at 0, 0, it's going to start at x equals 0, y equals 1. And otherwise look exactly the same, has exactly the same shape. Now, if you don't have this graph in your head, if you don't know what y equals the square root of x plus 1 looks like, you can always just plot points. I would choose perfect squares for values of x. So try x equals 0, x equals 1, 4, 9, 16, 25, and so on. And you can plot the points and then graph them with a smooth curve. And the curve is going to have that basic shape. So we're going to see something that looks roughly like that. That's y equals the square root of x plus 1. Now we want to know the moment of this lamina about the x-axis and about the y-axis. So that's a tendency of this whole system to rotate about either axis. When you have the moment about the x-axis, that's a tendency of the system to rotate about the x-axis. So you're almost thinking of the xy plane resting on some fulcrum that looks like this at x equals 0, y equals 0. And you've got this region, what looks something like this over in some particular region, right? And the question is, if this is the x-axis and this is the y-axis, does this does the mass of this planar lamina cause the entire system to rotate about the x-axis? So does it rotate to the to the top or to the bottom here, or like to the left or to the right, if we look at it in that way? And then when we talk about the moment about the y-axis, well, that's a measure of the tendency for the entire system to rotate about the y-axis. Now, I think we all know that if we have some mass that is lying here in the first quadrant where x and y are both positive, that is going to cause like this little piece of paper to just sort of like pull down in this direction. So it's going to have a tendency to rotate about the x-axis this way and a tendency to rotate about the y-axis that way. We want to measure those tendencies with these expressions, or actually it's going to be a number, or two different numbers, and each of those is called a moment. And then x bar, y bar is where we could place the fulcrum instead so that the entire system balances and so that there's no rotation over any axis. Okay, so that's the idea. That's what we're getting at here. Now, one of the principles from physics that we're going to use is that the total moment acting on some system is just the sum of the moments. It's a superposition principle. So one way that we can find the moment about the x-axis is not by thinking about finding the moment of the whole thing, not initially, but instead by breaking this into little pieces and then thinking about the moment of that piece about the x-axis. And so I'll denote that if that's the ith rectangular slice by m sub x sub I. And it turns out that that moment about the x-axis, if the x-axis is fixed, is defined to be the mass of that piece times the average distance between that piece and the x-axis. And it's the distance to the x-axis because we're looking at the moment about the x-axis. Now, if you've taken physics, you might think, well, isn't it force times distance? Yeah, we're just leaving off gravity here, even though gravity is implied. I'm not really sure why we think of mass times distance rather than force times distance in calculus class, but we do. It's convention. Okay, so we want the mass of that piece times the distance of that piece to the x-axis. The mass is actually pretty simple. We were told that our lamina had a uniform density rho. Uniform just means that that's constant. And since we're talking about a lamina, that's going to be in units of mass per unit area. So if I want mass of this piece, all I have to do is take the density, which is mass per unit area, and multiply by the area of that piece. And mass per unit area is given by that Greek letter rho. And the area is actually pretty simple. If this is my top function and that's my bottom function, that's delta x right there. The area is this change in y times the change in x, but the change in x is delta x, so we want this change in y in terms of x. So we're going to have the top function in terms of x minus the bottom function in terms of x. It's the top y value minus the bottom y value. That's our change in y times our change in x gives us the area of that little rectangle. And that combined with rho, when we multiply those together, that gives us the mass. Okay. Now we want to take that and we want to multiply by the distance to the x-axis. Now, if you're like me, you might think, well, there's lots of distances to the x-axis here. I've got an entire rectangle. One of the distances to the x-axis is to the distance between the x-axis and that innermost edge. And then there's the other one between the x-axis and the outermost edge. Say, well, which one are we supposed to use? Well, we're going to simplify this problem of finding the distance to the x-axis by looking at the centroid, or the center of mass, of that little rectangular piece. Since our density is uniform, the center of mass of this rectangle depends on geometry. It has absolutely nothing to do with a distribution of mass on the rectangle itself. So the center of mass will be at the average x value and the average y value. So it's kind of exactly where you would think it would be, like right there in the middle. So the distance to the x-axis is going to come from that middle point in our rectangle down to the x-axis. So that's a top y value minus a bottom y value. The top y value is just the average y value between these two y values. It's that one plus that one divided by 2. That would give us the average. And then we're going to subtract 0, which does nothing. So the distance to the x-axis is the top y value plus the bottom y value. And then you divide that by 2. It's just like taking an average. You had 2 test scores, you add them together and divide by 2. That's exactly what we're talking about here. So this distance to the x-axis is actually a y value. And because we have lots of y values, we're going to take the average y value. And that actually makes sense because the center of mass is a property of the geometry of that rectangle, and not is not changed by a distribution of mass that is non-constant. Okay, so this is the moment about the x-axis just in general, but we can simplify this. If you have a minus b times a plus b, hopefully you remember from pre-calculus that that's just going to be a difference of squares. First times first is a squared, outer times outer, and inner times inner cancel out. You got an ab minus an ab, so those are gone. And last times last is the negative b squared. So that's what we're going to have right here. So we have rho times 1/2. And then you have f minus g times f plus g. So that f of x is acting as our a, and g of x is acting as our b. And then don't forget your delta x, and we put that on the far right. So that is the formula for the moment of that piece about the x-axis. And then because of the superposition principle, it turns out that the total moment about the x-axis for the entire thing is the sum of those moments. So if we have n rectangular pieces, we would find the moment for each piece. We'd add those together. That would give us an approximation of the moment of the lamina about the axis. And if we want the exact moment of the lamina about the axis, we can take the limit of that sum as delta x goes to 0. Or alternatively, if you're thinking of all those delta x's being the same size, you could let the number of rectangles go to infinity, and that will lead us here. So you have an integral. Got rho over 2 times the top function squared minus the bottom function squared. Delta x becomes dx in the limit, and the top function is the square root function. We can see that that's the top function just from our graph. It's the one associated with the higher y values. And the bottom function is our line. Now we also need limits of integration. Clearly we started at x equals 0 because when x equals 0 on the line, y is equal to 1, and when x equals 0 on this square root curve, y is equal to 1. We need to find the other x value and figure out what that x value is right there. In order to find that x value, you can set the y values equal to each other and just solve for x. So we've got 1/5 x plus 1. That's the y value on one curve or on the line. That has to equal the y value on the other curve at the point of intersection, because those y values are the same at that location. To solve this, we'll subtract 1 from both sides. And then to get rid of the squaring function, we'll undo that by squaring both sides. When you square the 1/5, you're going to get 1 over 25. If you take the square root of x and you square it, you get x. And then you might multiply both sides by 25 to clear the fractions, and then subtract 25x from both sides. And then you see we've got a polynomial equation. It can easily be solved by factoring. These two terms have an x in common. X times x would give me x squared. X times negative 25 would give me the negative 25x. And this times this equals 0 if the first factor is 0 or the second factor is 0. And if you add 25 to both sides, that's what you'll get. X equals 0 and x equals 25. So x equals 25 is where those intersect. That's what that tick mark is right there. Okay, great. So we've set up the equation for the moment about the x-axis, or the integral representing the moment about the x-axis. Now we just need to evaluate this. So we're going to do some algebra. And I would recommend bringing out that 1/2 in the row. So square root of x plus 1 times square root of x plus 1 minus 1/5 x plus 1 times 1/5 x plus 1. First times first here is square root of x times the square root of x. That's just x. It's like the square root of x squared, so those will undo each other and you'll just get x. Outer times outer and inner times inner are the same. So if square root of x plus square root of x, that means we're going to have 2 of those. And then last times last is just 1. And then over here, get a minus sign. First times first is going to be that 1/5 x times 1/5 x. Multiply the constants first, the coefficients first. 1/5 times 1/5, you just multiply straight across. You get 1/25. X times x is x squared. Outer times outer and inner times inner. It's 1/5 x plus 1/5 x, so that's going to be 2/5 of x. And then last times last is a 1. And of course, you want to distribute that negative. And we'll have rho over 2 times the integral from 0 to 25 of this. Now, a square root can be written as a 1/2 power. This is the x to the 1/2 power. Now, if you don't remember how that works, it's x to the m over n is the nth root of x to the m. This number is the index of the radical, and then this number is the power inside. So there's an implied 1, that's an x to the first, and with a square root, that's an implied 2. So we end up with x to the 1/2. And then we need to distribute the negative over here. And of course, the 1s will reduce. And we have this. Excuse me. Now the 2 times x to the 1/2, I don't have anything like it. So I'll write that down. And then I don't have anything like the negative 1/25 of x squared. But this x minus 2/5 of x is going to leave us with 3/5 of x. That's like 5/5 minus 2/5 is 3/5. Okay. And now from here, we just want to use the power rule. So bring the 2 down, then you want to add 1 to the exponent and divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Then bring the 1/25 down. Then we'll add 1 to the exponent and divide by the new exponent. Bring the 3/5 down. There's an implied 1 there. Add 1 to the exponent, divide by the new exponent. And then we'll evaluate from 0 to 25. And then you can simplify, of course. There's an implied 1 there, so that's 4/3. If you want, you don't have to do this, but if you want to, you can think of that x to the 3/2, it's x to the 1.5, as x times the square root of x. And we multiply straight across there, so you've got 1/75. And here we have 3/10 times x squared. We'll evaluate from 0 to 25 and see what we get. You have 1/2 of rho times, so I kind of lost the rest of that. It's 3/4 times x times the square root of x. I said 3/4, but it was 4/3 x times the square root of x. Minus, let's see, 1/75 times x cubed. So that's 1/75 times 25 cubed plus 3/10 times 25 squared. And then if we evaluate all of that at 0, we're going to get 0. So that's our answer. Now you can do the arithmetic if you want to, but you don't have to. This is 4/3 times 25 times 5. And then we've got 3 times 25 down here and 25 cubed up here. So one of those will reduce. And then the 10, of course, you could simplify that as well. That's 2 times 5, and 25 squared is 5 times 5 times 5 times 5. So one of those 5s will reduce. So we end up with this. Looks like I've got 4/3 times 5 cubed minus, that's going to be a 5 cubed times an extra 5. Whoops. 5 cubed times 5 over 3 plus 3 over 2 times 5 cubed. And again, the reason why I did that was because I want to simplify this in my head. Now I've got multiples of 5 cubed. So I've got 4/3 of 5 cubed minus 5/3 of 5 cubed. So that's going to be a negative 1/3 of 5 cubed. And then over here, we're adding 3 over 2 times 5 cubed. Because we need a common denominator, so we'll multiply by 3 over 3 here to make that denominator a 6. Multiply this one by 2 over 2. And so what we end up with is 5 cubed times a negative 2/6 plus 5 cubed times 9 over 6. And if we do that arithmetic, we end up with 7 over 6 times 5 cubed. 5 times 5 times 5 is 125. And we end up with 7 times 125 times rho. So it's going to be 700. And then let's see, if you had 7 quarters, that would be $1.75. So we'll have 700 plus 175. So it's going to be 875 times rho, all divided by 12. And I don't believe that that simplifies at all. Okay. So that was a lot of arithmetic. Of course, when you get to this point, you can use your calculator, but it's always a good idea to practice your arithmetic so that you don't lose it. It's definitely one of those things. If you don't use it, you'll lose it. Okay, so we have that. Now let's find the moment about the y-axis. The idea is the same. This time though, instead of looking at the moment of this piece about the x-axis, we're going to look at the moment of this piece about the y-axis. The moment is going to be equal to the mass times the distance, but this time the distance is to the y-axis as opposed to being the distance to the x-axis. So that's our distance to the y-axis. Well, that distance to the y-axis is actually an x value. If you're not sure that you believe me, think about it. If we're at the point x equals 3, y equals 2, this distance from here to here is actually the x value, right? So that's going to be an x value in general. So if I'm at some ordered pair x, y, the distance from here to here is x, and the distance from there to there is y. So when we find the moment about the y-axis, we're going to do this, but we'll have y-axis instead of x-axis, and the distance to the y-axis will be x. So we'll have the mass, which is rho, that's mass per unit area, times area, which is the top function minus the bottom function, times dx, or delta x. So this is all mass, and then the distance to the y-axis is x. So our formula is going to look like this. But again, that's just because this is mass per unit area times area, which gives us mass. Mass times distance gives us this. And that's enough for us to set up the integral. We're still going to integrate from 0 to 25. That's our range of x values. Then we'll have an x there, and then the top function is the square root of x plus 1, and the bottom function is 1/5 x plus 1. So if we distribute that negative again, the 1's are going to reduce, and we'll have the integral from 0 to 25 of rho times x times the square root of x, which is x to the 1/2, minus 1/5 x. And if you distribute that x, we'll have, when you add the exponents, 1 plus 1/2 is 3/2. And then x to the first times -1/5 x to the first is -1/5 x squared. Okay, so that is our moment about the y-axis integral. We just need to evaluate it. It's not too difficult. We're just going to use the power rule. So add 1 to the exponent. 3/2 plus 1 is 5/2. And then you want to divide by the new exponent. Then bring the -1/5 down. Then add 1 to the exponent and divide by the new exponent. Then evaluate at 0 and 25 and subtract. And again, I'm going to use that same trick as before. This 5/2 is 2.5. So it's going to be an x squared times the square root of x, because that's the second power and that's the 1/2 power. So what we have this time is rho times 2/5 times 25 squared. And the square root of x is the square root of 25, which is 5, minus 1/15 times 25 cubed. And then when we evaluate all of that at x equals 0, we just get 0. The 5's reduced there. And we end up with 25 times 25, which is 625. And you take 625 and you double it. So that's going to be 1250. And then over here, we're going to have a -1/15. That's 1/3 times 5. And then 25 cubed is 25 times 25. And then the third 25, I can factor as a 5 times 5. That way one of those will reduce. We'll be right there. And so now we've got 1250 minus this 625 times 5/3. Actually, in that case, it might be helpful to write this as 625 times 2. And we want a common denominator. So I want this denominator to be a 3. So I'll multiply by 3/3. And then I'll have 625 times 6/3 minus 625 times 5/3. And then 6/3 minus 5/3 is, of course, 1/3. So we end up with 625/3. And somehow I lost my row. So we're going to multiply by row. Okay, so that's the moment about the x-axis. That's the moment about the y-axis. And we can put those two pieces together to find the center of mass. The x bar, that is the location of our center of mass, our new balance point, so that the entire system could rest on that point and the whole thing doesn't shift to the left or to the right anymore. It would just balance. X bar turns out to be given by the moment about the y-axis divided by the total mass. And y bar turns out to be given by the moment about the x-axis divided by the total mass. It's counterintuitive that the x value has the moment about the y-axis and the y value for your center of mass has the moment about the x-axis. But I think that if you remember where these formulas come from, it makes sense. The moment about the y-axis, the moment about the x-axis involved a distance to the x-axis, but that distance to the x-axis was a y value. And when we found the moment about the y-axis, the moment about the y-axis involved a distance to the y-axis, but the distance to the y-axis was an x value. So these distances were sort of the opposite of what we would expect, which is why these formulas involve moments that are sort of the opposite of what we would expect. Now we have both of these moments, but we don't have the total mass. The total mass is easy to find. If you were to find the mass of one piece, or if you want to find the mass of one piece, you're just going to take the mass per unit area and you'll multiply by the area of that piece. And mass per unit area is given by our uniform density rho, and the area is just the area of that representative rectangle. So it's the top function minus the bottom function times delta x, just in general. Just like we had right here, mass is just this piece. Now, if I want the total mass, I'll take all of those rectangles, I'll find their masses and I'll add them up, and I'll take the limit as delta x goes to 0, or if all those delta x's are the same size, you can let the number of rectangles go to infinity. And so we end up with rho times this integral. And I hope you notice that this is just a constant times the formula for the area between the two curves. The top function is that square root function, and the bottom function is the line. When we distribute the negative, the ones will reduce. And we'll have this. You can write that as a 1/2 power if you want. Well, I would recommend that so that you can use the power rule. Okay, now we're going to add 1 to the exponent. 1/2 plus 1 is 3/2, and then divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Then we'll bring the negative 1/5 down. You've got an x to the first here, so you're going to add 1 to the exponent and then divide by the new exponent. Substitute in 0 and 25 and subtract. So we've got 2 over 3 times 25 to the 3/2. So that's going to be 25 to the first times the square root of 25. And this is 25 squared. And I'll write that as 25 times 5 times 5, so that one of those 5s will reduce from here. So it looks like we've got 2/3 times 25 times 5, which is 125, minus 1/2 times 125. So that's 125 times 2/3 minus 1/2, or if you want, and I do want to, you can get a common denominator. I'll multiply this one by 2 over 2 so that the new denominator is 6, and I'll multiply this one by 3 over 3 so that the new denominator is 6. It's like I'm taking my pie and I'm breaking them, all those pieces, into more pieces so that all the pieces are the same size. And then that means I've got 4/6 of a pie over here, and I'm subtracting 3/6 of a pie. And so I end up with 1/6 of that. So we end up with 125 times rho divided by 6 as the mass of the whole thing. Now, we weren't actually asked for the mass, but we need the mass in order to find the center of mass of our lamina. Okay, so let's find that center of mass now. Take the moment about the x-axis, or excuse me, the moment about the y-axis. And the moment about the y-axis was 625 rho divided by 3. And then we're going to divide by the mass, which is that 125 rho over 6. And then the moment about the x-axis is 875 rho over 12. And then we're dividing by the mass, that's 125 rho over 6. That's our answer, it's just not simplified. You can, dividing by this fraction is multiplying by the reciprocal, so multiply by 6 over 125 rho. 3 goes into 6 twice. 125 goes into 625 5 times. The rows reduce. So we just get 10, okay, for our x value, for our center of mass. And then over here, we're going to do something similar. Multiply by the reciprocal. 6 goes into 12 twice. The 2 rows reduce. And then 875, that's 32 If I have $8, you might say, how many quarters do you have? Well, you'd have 8 times 4, 32 quarters, plus 3 more for that 75. So that'd be 25 times 35 there over 2 times 125 in the denominator, or that over 2 times 1 over 125, which is 25 times 5. And the 25s reduce. And 5 goes into 35 7 times. And so what we get is x bar equals 10 and y bar equals 7 over 2. And that's it. So let's go through that one more time, just to make sure you understand how this works. If you want to find the moment about the x-axis or the y-axis, the first thing you need to do is graph the region, just to visualize what's happening. And then you have to remember that when you're finding a moment about the x or y-axis, the way we do that is we find the moment for each piece. And what we tend to do is we tend to take our lamina and break it into little pieces. And those pieces are usually rectangles. They could be vertical rectangles or horizontal rectangles. Now, to find the moment about an axis for that particular piece, you're always going to take the mass of that piece and multiply by the distance to that axis. The mass will always be the density times area. Most of the time in textbook problems, the density is just rho. It's mass per unit area, and it's not even given as a function of x most of the time. So you just have this constant here. And then the area is found the same way that you would find the area of any rectangle. So if the rectangles are vertical, you're just going to take the top function minus the bottom function and multiply by delta x. If they were horizontal, you'd multiply, or the delta y by the right function minus the left function. But you just find the area of that rectangle, and that's going to go there. And then the distance to the x-axis and the y-axis will depend on the geometry as well. But in this case, the distance to the y-axis is the x value. The distance to the x-axis is the average y value, which is that 1/2 of the top function plus the bottom function. You use those to derive the formulas, and then you set up the integrals. As a result, you may have to find points of intersection if it's not obvious by setting the two y values equal to each other. And then you just do some algebra and evaluate the integral using the fundamental theorem of calculus. And once you do that, if you want to find the center of mass, you've got to find the mass of the original lamina, which is really just this mass per unit area, or the density, times the area of the lamina. And the area of the lamina is just the top function minus the bottom function, times delta x, or that's the area of that rectangular piece. Now, when we add all of those together and take the limit as the number of rectangles either goes to infinity if all the delta x's are the same size, or if all the delta x's go to 0 if the delta x's vary from rectangle to rectangle. And you end up with this integral here. You evaluate that, take each moment, divide it by the mass, make sure they're in the right place to get your x bar and your y bar, and then this is your answer. In our case, we have x equals 10, y equals 7 over 2, that's 3.5. Let's look at our region. What this is saying is that the center of mass occurs at x equals 10, so that's about 2/5 of the way over here, and y equals 3.5. And when x is equal to 25, y is going to equal 6. So I think that 10 and 3.5 sounds reasonable as the center of mass. I could imagine putting the fulcrum directly under that location and the entire thing balancing on that point. So, it's always good to check at the very end and make sure that your answer actually seems reasonable. And this time it does.